In order to make these programs happen, we are fortunate to have a whole bunch of excellent sponsors. And tonight, our featured sponsor is Colorado, the donut company. But this is the one night we don't have their donuts. So enjoy some cookies. And we also have a really special sponsor of our series here tonight who is actually lodging our guest, Aria's Loft, which is over on Euclid Street. Marty and her husband are so generous as to donate 2 nights of lodging for our speakers. So thanks to them and all these others. So when you, yeah. I'll come over. We do pass around a clipboard. I know this is a repeat message for many of you who come every week. It is important that your name ends up on that list because our sponsors appreciate knowing how many people come. And that accountability to our sponsors is really helpful. So when that clipboard comes around, please add your names. And also, next week, I'll tell you a little bit about next week before I tell you about tonight. Robbie Andrews is a Colorado Ph.D. student in Boulder, University of Colorado in Boulder. And he'll be speaking about spruce beetles and how they make forest fires more severe or maybe not so much. So that'll be next week. We'll be talking about the impacts of beetles and impacts of beetles on fire severity. So that should be very interesting. Tonight we have a really special speaker because the Wilderness Workshop, one of the many projects that we do is we do wilderness monitoring. And we do this in partnership with the National Forest, of course, because the National Forest manages our wilderness areas like the Maroon Bells Snowmass Wilderness. But we, as a partner nonprofit, are able to help them out. And one of those programs that we do is we collect water samples at really high mountain lakes, Tabor and Brooklyn lakes, which are way up Lincoln Creek Road, and then Avalanche, Moon, and Capitol, which are just over Sopris over there. And there's a few people, or this data gets collected, sent to the Forest Service labs, and goes to these massive repositories, and you always kind of wonder who's going to use any of this data. But it's important, right? So we tonight have a scientist from USGS who has been using our data for years. And I also want to point out a couple people that were key in getting this going in our valley. And that's Susie Ellison, who helped to start this program back in the...
I didn't start it, but
you were instrumental in the 70s? 80s. And then retired hydrologist from our National Forest, Andrea Helen Sears, was instrumental in keeping the program going until she retired, and she's still very interested in keeping it going. And Andrew Larson, our wilderness ranger from the White River National Forest here, he's not here tonight, but he's keeping it going. I personally helped keep it going. I got some water samples this summer. So it's pretty cool. But a little bit more about Jill. She's an ecosystem ecologist with the USGS, or the U.S. Geological Survey, and a senior research ecologist with the Natural Resource Ecology Laboratory at CSU. She told me that what's important to tell you is that she loves playing in mountains. She loves places like up by Ashcroft and going up in those mountains in the winter and in the summer. And one of her newest things is she's the new director of the North American Nitrogen Initiative, and she's working on projects all over the world, and it's a joy to have her here. And so without further ado, I'll let her tell her story. So thanks for being here.
I want to thank Sarah for inviting me, and Marty and Chuck for letting me stay in this really great place. As they know, I have these large dogs, and the dogs have yellow fur, and your couch is a magnet for the yellow fur, even if they're not on there. But we'll take care of it. And thanks to all of you for coming out. I know that some of your previous talks this year have been related to foxes and birds, and that's exciting stuff, especially even to me. And chemistry, people often go, really? But it's fascinating, and what I'm going to try to do is show you why it's fascinating and why it's an interesting problem for us all to be thinking about. So without further ado, we'll try to move ourselves into the next slide. Go.
Is it not working?
No.
Oh, that's bizarre.
Go, go, go.
Exit this show, maybe.
Let me try this. Is that excellent?
Yeah, start again.
Okay.
That's weird. Maybe I didn't push the right way to do it.
I don't know.
Because I didn't do it that way. There it goes.
Yeah, but now it's blank. Where are the rest of my slides?
Okay, hold on.
Okay, what I'm going to do is start telling you about the next slide. Because when you think of global change, many of you think, rightly so, about climate change. And there are really, according to a number of international researchers, many types of global change. Some of them you could think of land use change, carbon dioxide emissions, pollution.
Do talk into the microphone, otherwise I can't hear you.
Okay.
Some other people can't hear you. We hear you.
Okay, but in a study that was recently done, there we are. In a study that was done in 2009 and then revisited again just last year, a group of scientists from all over the world said, what are the boundaries beyond which we can monkey up our planet and then be very sorry? So what is the safe operating space in which humanity can live on this planet? And at what point do we cross those thresholds with respect to our global changes and then enter a planet that we're not sure of, a planet that's going to give us unexpected types of changes? And so they actually came up with three parts of our global change manipulations as people on this planet that they said were worrisome. And here are the three. The first is climate change. It's right up here. And what you can see out here is the postulated planetary boundary beyond which we better not go, because we'll enter some sort of novel climate. And that's what you hear all the time when you hear about climate change news. And it suggests, according to this particular paper in 2009, that we're about halfway to reaching a boundary. You know, it's the 2.5 degrees centigrade that we all don't want to cross. The two others, though, that we actually have crossed, one is atmospheric nitrogen and water nitrogen. It's nitrogen pollution. It's creation of usable nitrogen on the planet and then putting it in places where we don't want it to go. And I'll tell you why we don't want it to go these different types of places. And the third is biodiversity loss. And many of you have heard we're in the 6th grade extinction, and a lot of that is due to land use change. And actually quite a bit of it is also due to atmospheric and water quality nitrogen excess, because nitrogen kills off biodiversity. And I'll talk a lot more about that later. So this is a major global change. And why it hasn't gotten the kind of publicity, as director of the North American Nitrogen Center, I have no idea, because this is so exciting. But we'll talk about the nitrogen. I'm not going to tell you, I promise, a nitrogen cycle over time. But I am going to give you a nitrogen story. And actually in Colorado, it's all about livestock. But through other parts of the world, it's largely livestock and agriculture over time. So why it's all about livestock in this state, and why it's all about livestock in many parts of the world, is because we all like to eat meat. And as other countries around the world become more affluent, certainly China, India, South America, and Africa, well, Africa always ate meat, they also like to beef up, pardon the expression, the meat in their diet. And we end up with feedlots like this. This actually, these are, that one down there is east of Fort Collins in Weld County, which is one of the richest counties in the world, certainly the 4th largest in the nation for cattle on feed. We have tremendous amounts of cattle. Well, we feed these cattle lots of grain. We feed them lots of nitrogen-producing plants. They produce the nitrogen, which is the proteins that we like to eat in the meat. That's what makes umami and makes things taste good. And they excrete a tremendous amount of that because they're highly inefficient. So I went into more detail about nitrogen, but to show you what's going on with respect to feedlots in Colorado, this is Colorado. Here's some feedlots over here, over by Grand Junction. But this is northeastern Colorado, just east of Rocky Mountain National Park and the Colorado Front Range. And the size of the blobs are the size of the feedlots, not only feedlots, but dairy. And as you can see, we're a real hot spot all on the planet for animals on feed. And again, Weld County is, I think, number 1 or 2 in the nation for cattle on feed. I might have just said 4th. They're extremely, it's a success story that got away, because it makes them very affluent. partly because they can grow the crops right there and feed it to the animals right there and slaughter them right there. So they are tremendously profitable, but we end up with an awful lot of manure this way. And the manure is a large part of what I'm going to be talking about today. But let's step back and look at nitrogen back in the day. This is somewhat before the Industrial Revolution, or right about at the tip of it, and nitrogen came from a very few number of natural sources. Now, some of you may go, wait a minute, the atmosphere is all nitrogen. And that's true. 78% of what's up here is N2 gas, but it's not usable. So nitrogen, for all of us, every living thing, is the stuff of DNA. It's the stuff of amino acids. We all need it in order to grow proteins. Thank you.
It's not picking you up.
I'm sorry.
There you go. You really have to talk into it. You should
Okay.
use yourself in the microphone.
I'm sorry.
That's okay.
So we all need nitrogen in a big way. And it was inaccessible up until about the Industrial Revolution because it only was made accessible by tremendous amounts of combustion. And you can get that from lightning, which would take the atmospheric nitrogen, which is not accessible. It's two nitrogens bound together with a triple bond, and it takes a lot of force to break them up. So lightning was a way to bust that up and make that nitrogen reactive or usable by animals and plants on Earth. And as I said, we all need this. It's the stuff of proteins. The other ways in naturally is you can get it from biological nitrogen fixation. These are legumes. These are nitrogen-fixing nodules on soybeans, and any kind of bean is a nitrogen-fixing. There's also cyanobacteria that fix nitrogen, and they do that by putting a lot of energy into busting up those nitrogen bonds from atmospheric nitrogen. So about 140 teragrams, that's a large number. That's what was produced naturally from both crop nitrogen fixation, basically alfalfa, and natural nitrogen fixation. If you fast forward to today, we've almost doubled our available nitrogen that's reactive. In the United States, we've increased our reactive nitrogen by more than 5 times what was natural before. And you can see that some of these colors have changed. So first of all, natural nitrogen fixation, which was the bulk of it before, is now, maybe a third of it now. Natural nitrogen fixation coming from croplands. Crop nitrogen fixation here has come up a little bit. These are crops that are planted for nitrogen. And then we have some new sources here. So fossil fuel combustion is another way of combusting. Here's lightning, it's still there, but it hasn't increased over time. And fossil fuel combustion now takes the role of that and magnifies it by putting large amounts of energy in a small space, and you can bust up the atmospheric nitrogen and make it available. So fossil fuel combustion comes from power plants, comes from automobiles, it comes from construction vehicles, trains, all of those things are sources of that particular type of reactive nitrogen. But over here is the bulk of what's coming out, and this is synthetically produced fertilizer. So I'm going to talk a little bit about how interesting this is because the ability to produce synthetic fertilizer started out as the ability to produce dynamite, and it's called the Haber-Bosch process. You don't need to know that. But what it does is it allows the use of fossil fuels to break up the atmospheric nitrogen and turn it into ammonia, which can then be used to put on crops. And this is a good thing. We have 7.4 billion people on the planet, whether you think that's a good thing or not. We can feed most of them because of the Green Revolution. The Green Revolution not only used better seed varieties, but largely this available nitrogen in order to feed all these people. So we've gone from worldwide 140 up to 270 teragrams. All that reactive nitrogen is flowing around. So parts of it are a good thing, but parts of it are not. So this is called the nitrogen challenge because we want the crops, we want the fertilizer, we want to grow the food that we all want to eat. More and more people want us to take that food and feed it to beef cattle and then eat the beef as well. But it has all of these other unexpected consequences. So by applying this nitrogen or putting it in, having it come out of our tailpipes, we end up with things that we don't want to happen. And this is why nitrogen is such a problem. So the Green Revolution was a good thing. It gave us the amount of food that we have available on the planet. There are some problems with that. I'm not even going to talk about it. But because it's cheap, So synthetic nitrogen fertilizer price rises and falls with the price of oil. Right now, oil is very cheap, which makes nitrogen very cheap. It's really good insurance if you're a farmer in order to put nitrogen on your crops, because you can put it on, the plants grow better, you get a very high yield. But the plants themselves are inefficient. Not as inefficient as cows, but they're inefficient. So no matter how much you put on, some of it's going to leach out the bottom or go up into the atmosphere. And that's the problem that we have in Colorado. So we're getting this sort of, I didn't mean it, extra nitrogen flowing into the environment. So when you put it on your crops, you grow crops better, but when it leaches out, you get all kinds of effects on water quality. Some of that is a fertilizer. Nitrogen's a fertilizer. You put it in water, you're going to get green rivers and lakes. That's eutrophication. That's the process of increasing the nutrient load that increases the plants there. If you get extreme eutrophication, you can get dead zones. We have dead zones in every major estuary in the world where there's agriculture. The Gulf of Mexico is the poster child for the United States, but Chesapeake Bay as well. That's a nitrogen problem. It's too much nitrogen going into groundwater, leaching into lakes and rivers, and moving out into the estuaries. It's also a bummer for human health. You've all heard of blue baby syndrome. That's when groundwater is drunk or surface water with water quality with nitrogen that's greater than 10 milligrams per liter. That's the EPA standard. It actually interferes with the oxygen uptake in babies. That's a problem that's been known for many years. 30% of the groundwater that's used for drinking water in this country has water quality levels higher than that level. So these are people at risk, their children are at risk, and increasingly we're finding out that it's also a cancer-causing agent, especially in women. So high nitrate in your groundwater is a bad thing, and it's exceedingly common in the United States. I mentioned before that when you add nitrogen, you grow plants better. Well, you grow some plants better, and some plants lose out. So there's winners and losers, and it's a major reason for the loss of biodiversity, particularly in developing countries right now that are just beginning to add nitrogen to their environment. But it's also a problem in this country, and I'll give you examples from here. So what else happens? When you put it up into the air, you get all kinds of nasty things. Major smog. Nitrogen oxide, which is the stuff that comes out of tailpipes, is the precursor to smog and ozone. And it looks like that. That's actually a picture of Denver back in the day. And it is a huge determinant of respiratory ailments. And there have been amazing studies that have calculated that if we were to reduce the ozone and the smog that come out of nitrogen oxide and power plant emissions, billions of dollars in health savings would happen. So we have a human health direct relationship to nitrogen release coming out of power plants, out of transportation industry. And ozone is also severely affecting crop loss, and natural plants are affected by it as well. So it's not a good thing to have this stuff go into the atmosphere. But that's not all. Unfortunately, some of the nitrogen that goes up into the atmosphere actually turns into a greenhouse gas. So I'm giving you this litany of terrible things that are happening to nitrogen, and people never think about it. They think about the green revolution, which is a good thing. But when you get N2O, that's laughing gas for those of you who are a dentist or go to the dentist, when you get N2O going up into the atmosphere, it is a potent greenhouse gas. It's 240 times more strong than carbon dioxide, which is what we all think about when we think about global warming. There's more and more N2O going up into the atmosphere as the Arctic warms, and you get melting up there. There's an N2O source from there. There's also an N2O source from rice paddies as we grow more and more rice. This is a process that comes out of waterlogged systems over there. And of course, right in the middle of it, anytime you add nitrogen to these systems, you're going to reduce biodiversity. So these are all the reasons why the nitrogen cascade from adding it to grow our crops has become a problem, a global problem. And just to show you that it's a global problem, what I'm going to be talking about, of course, is Colorado, and I'm going to get there next. But everywhere that there's red and orange on this map, there is way too much nitrogen flowing into these ecosystems, reducing their diversity, causing human health problems, all of the things that I just mentioned before. So developing countries that have tremendous agriculture, India and China, actually you get to places in northeastern China and in parts of India where the devastation is extreme, you can dial it back by reducing the nitrogen. But for now, countries that are developing are adding more and more fertilizer in order to grow the crops they need, and it's becoming a problem. It's becoming a problem in parts of South America and Africa as well, as these nations try to catch up. They are nutrient poor to begin with, and they do not yet share in the benefits of the green revolution. So they want to catch up. They're adding more fertilizers to their crops. In many cases in South America, they're adding this to grain crops that are then fed to cattle, that are then turned into hamburgers that are sold all over the world. But they're getting there too. So pretty soon it's going to be even more of an issue globally than it is right now. Let me come back and talk about Colorado. So one of the first questions people always ask me is, how much deposition is actually falling? You know, is this really a problem in Colorado? And if you just look at the box and you look at the colors, you'd say, well, no, maybe it's not. It's probably obvious, but the darker the color, the oranges and reds, the greater the nitrogen deposition. So I'm shifting now to talk not just about water quality, but mostly what comes up into the atmosphere and transports and falls down in rain and snow. That's deposition. And the reason I do that is because in the mountains in Colorado, that's our source of pollution. We are so lucky living up at the top of the watersheds that we don't have agriculture above us in many cases. What we have is what falls out of the sky. So our global changes in the Rockies are, yes, there's some tourism, but mostly it's climate change and it's atmospheric nitrogen deposition. So you look at these numbers, and in Colorado, the numbers range from about 1 to, if you go to the yellow, on the eastern plains, out by the Pawnee grasslands, out by Weld County, it gets up to 10. If you look at the rest of the country, you can see that a lot of this nitrogen is in congested, heavily populated areas. That's areas that have a lot of industry, a lot of power plants, a lot of cars. You could see the Great Plains here, lots of nitrogen emitted here and falling down from agricultural areas. I don't want to dismiss the Central Valley of California and also up in Salt Lake area, but by and large, Colorado and the West, as you move further west, is cleaner than the rest of the country. So you'd go, what's the problem? Why is there a problem? And again, our deposition, especially up in the mountains, goes from about 1 to 6 kilograms of nitrogen per hectare, compared with down here, 18 to 20 kilograms of nitrogen per hectare where there's a problem. Well, I'll show you what our data actually look like. And we have been measuring and monitoring the precipitation chemistry in the Rocky Mountains for many years. Some of these early sites started in the 1980, I think was some of the earliest. In Loch Vale, which is my own research site in Rocky Mountain National Park, we started in 1983. But I'm starting here with 1989 because your local deposition monitoring program is Sunlight Mountain, and Sunlight's right down here. So Colorado actually has a distinction of having more of these national atmospheric deposition program sites than any other state in the nation, which is great for us. And part of it's because we have so much topographic relief that if you measure down here in Carbondale, you're not getting any clue about what's falling up on top of Mount Sopris. So we have lots of paired sites, high and low depth elevation, and that helps us in trying to figure out what's going on, because we really do have a problem. Well, I should say, I really have a problem on the Colorado Front Range. Our long-term record shows that our deposition is somewhere around 3 to 4 kilograms per hectare. We're still trying to figure out what happened in 2013 with that very high peak. Your deposition over here is much cleaner. So partly tonight I'm going to be telling you a good news story, because what we see over here on the western slope, particularly in the Roaring Fork Valley, is a lot cleaner ecosystems than what we see on the Colorado Front Range. And in a sense, that makes perfect sense. We have a lot more people, we have a lot more pollution, we have an awful lot more cows. But your deposition, this is both rain and snow, is hovering somewhere around 1.5 to 2 kilograms of nitrogen per hectare per year. That's still an order of magnitude higher than background values, but it's a good thing. It's very low. It's among the lowest in the United States. So these are still very low amounts of nitrogen. Why would you care? And it's partly because you look at systems like ours. This is Loch Vale, obviously, in the winter. There's no soil up there. So nitrogen, I've mentioned before, is a fertilizer. If you could trap that nitrogen when it falls out of the sky, it wouldn't cause any damage. So if you could suck it up into trees and plants and microbes, life is good. Those trees and plants and microbes would be growing better, and that stuff wouldn't be left loose to flow into your streams or go up into the atmosphere. But if you don't have any plants, if you don't have any soil, you're not going to be able to store the nitrogen that's coming in. So we have a problem in Colorado even with very low amounts of nitrogen because there's no soil, there's no vegetation. Winter is the norm up here, so nothing's growing while that nitrogen is coming in. And when it melts in the spring, you get this huge whoosh of snowmelt, and it all flushes down really fast. So again, the plants have very little opportunity to take it up and store it. And that's a problem by itself, and I'll talk about that in a second. What I want to do now is show you some of the things that we found over the years about what nitrogen is doing, and then when I can, make comparisons to over here on this side of the mountain. So if you are in Rocky Mountain National Park, this is Rocky Mountain National Park, over here, you get all these sources of nitrogen from the Colorado Front Range. There's lots of agriculture, there's lots of industry and power plants, there's lots of construction, and transportation over here. All these things put up this nitrogen into the atmosphere. It moves, in our case, well, actually in your case too, it moves from the plains to the mountains on a daily basis. It's this mountain breathing phenomenon where the plains heat up and the hot air rises up into the valleys, gets up to the mountaintops. In our case, it hits the tropospheric boundary where if there's moisture, you get condensation and you get afternoon thunderstorms, and it falls right down on the mountains. So that's basically how we get this kind of pollution. You certainly, every valley in mountainous areas in the world has this same kind of diurnal sloshing around of air. So as you have pollution, it's going to move up into your mountaintops. Luckily, you don't have very much yet. So we have been doing research in this particular watershed since 1983. I call it my third child because it takes about as much effort and it never goes away, unlike my children. But this is Loch Vale Watershed. It's in Rocky Mountain National Park. We selected it for a number of reasons, and it's been a great long-term research study site. We are in a national park, so our equipment is very simple, and of course it's Park Service brown. What we have are rain gauges. That rain gauge is actually 6 feet off the ground, but in the winter it looks sort of like that. Here are the famous buckets where we collect precipitation. We do this on a regular basis. We have stream gauges where we measure chemistry as well as flow coming through. We look at soil chemistry. We have all kinds of stuff going on. And we actually sample this every Tuesday. So we have been doing this since 1983. There's about 7 weeks out of that period when we couldn't get up there, but it looks like this on a day like today. And we get up there and we swap out those buckets for the chemistry. So we have 33 years now of this kind of record, and it's a long-term study site. What the Forest Service has done is also equally phenomenal. There are Forest Service long-term lake records all over the Rocky Mountains, Wyoming, Montana, Colorado. It's great because of volunteers who go out and collect these samples, you get the records that show you what's actually changing. We are lucky enough that we have been sustained here to do this long-term research. We've gone back in time to ask questions about what happened 12,000 years ago when the glaciers receded, what happened when the nitrogen started to increase, which by the way was 1950, I'll tell you that now. We've done experiments in the field and laboratory, we do modeling with computer models, and we do a lot of spatial comparisons over time. So we started looking out for acid rain. This was an acid rain study, and we didn't find any. Actually, the long-term monitoring of these lakes was an acid rain study. Was there acid rain in the Colorado Rockies? And the answer is no. But what we found instead was an awful lot of nitrogen, and it was like, that's funny. Why would there be this problem? So we started looking at what it was doing. And here's the punchline right now, and you could all nod off if you'd like. Everywhere we looked in this ecosystem and everywhere else along the Colorado Front Range, we found changes, and they were changes due to nitrogen over time. So I'm going to take you on a little tour. We looked in the Alpine. Now the Alpine is very special to all of us, and it's an international treasure. People come from all over the world to see the showy wildflowers in the summertime. But one of the things that has been found in grasslands all over the world, and the Alpine really is a grassland when you think about it, is that when you fertilize, some plants are winners and some plants are losers. And the plants that are winners in grasslands all over the world are grasses and sedges. And so they can take advantage of this nitrogen faster than the showy wildflowers. They grow tall and essentially shade them out. So here's an experiment that my colleague Bill Bowman did, where he added nitrogen to alpine plots, both on Niwot Ridge and in Rocky Mountain National Park. And over 5 years, what he found was a huge increase in grasses and sedges. This is carex, it's a sedge. So instead, what we're seeing is a transformation of the alpine from systems that look like this to systems that look like that. Those grasses are very happy. They're taking up the nitrogen and storing it, but the rest of us are not so happy coming in. So we're seeing changes like that happening right now on the Colorado Front Range. We're also seeing changes in our foliar chemistry of our needles. So this is a great Engelmann spruce. What we did for this is we did surveys, we did studies of paired sites in high nitrogen deposition sites, that's east of the divide, and low, which is west of the divide. And we paired them. They were all Engelmann spruce. They were all about the same elevation. They were all facing the same angle, slope angle. They were all the same age. And what we found is that where you get more nitrogen deposition, the needles have a lot more nitrogen in them. So you think about nitrogen, you think that it's the stuff of proteins and DNA. It makes these needles very attractive to insects that like to eat needles. Our trees right now in Rocky Mountain National Park are being devastated by spruce beetle, but these are bark beetles, and the pine bark beetle that came through 10 or 15 or 20 years ago. Those are bark beetles. Those are not the beetles that are going to get after these needles. But the needle-eating insects are going to go for the higher nitrogen needles. And research that's been shown in the eastern United States documents that it's delicious if you're an insect to eat the nitrogen-rich leaves and needles. We haven't seen that at all in this part of the country yet, but that's something that is a concern when you have too much nitrogen in these ecosystems. So we found that. We also found lots of changes in soil chemistry. That is a soil pit that Claudia boots in there. We had to dig down through the snow to get at it. What we found over the years is that the nitrogen has actually caused our soils to become more acidic. It's caused a lot of our carbon to change structure, and it has caused a change in the microbial function of these soils. So the microbes are down there. These are fungi, these are bacteria. They're good because they decompose, and if we didn't have them, of course, we'd all be up to our eyeballs in undecomposed dead things. So this decomposition is a really good thing. It's altered it, it hasn't reduced it. But what we're finding in this is that it's changed the mineralization rate. So I'm actually going to not go into this very much, but what we found is that there was a lot less of this microbial activity in sites that don't have a lot of nitrogen, and when you add it, it speeds them up. But what that's done is very interesting. It's actually changed the fungi and the bacteria in the soil, and now it's changed what eats the fungi and the bacteria. So we're working our way up the food web. We're actually changing it with the nitrogen that we're adding. So now the soil food web, is made up of fungi, bacteria, and then whatever eats them. Those are nematodes, those are mites, those are springtails. So what eats those? Snails, salamanders, birds, all of these things. So we're working our way up the food chain with changes in nitrogen. And we've seen very dramatic changes so far in at least that first level, the nematodes and things like that. So our soils are changing with respect to nitrogen coming in. One of the things that I am most interested in is what happens with the lake and stream chemistry. And we've seen lots of changes here. Basically, if you have very little nitrogen in your lakes, which is the case for here in the Roaring Fork Valley and in the wilderness areas surrounding us, if you add nitrogen, you fertilize it and you get algal growth. That's basically what this green line says here. If you don't have much nitrogen and you add it, they all love it. They grow. You get lots of algae going in. If you have a lot of nitrogen, such as on the Colorado Front Range, you can add more nitrogen and they don't care because they're limited by something else, in this case phosphorus. So when you add phosphorus, you get growth if you have high nitrogen lakes. So we did a survey actually of about 90 lakes in Colorado, and then we added another 1,000 from Scandinavia, and that's what all those points are there. And then we followed up with experiments, and I'll show you the experiments in a minute. But basically what we found is that you can change the nutrient status of these lakes by adding nitrogen, and it changes their algal composition. And I'll go work my way up the food web for that in a second. But just to show you some of your data from around here, I picked 2 lakes at random. No, I didn't pick Brooklyn at random because I've been there with Andrea, and it was the most amazing trip. This is a long-term time series of nitrate concentrations in early summer from lakes around here. So Brooklyn Lake is in the collegiate wilderness, Willow is in the Eagle's Nest, I want to say. And I picked the 2 of them. The year here is 1990, and this goes up to 2011 over here. This is 2010. I'm sorry about these numbers down here. And then I just picked one of our lakes that we've been studying for a long time too, Hayaha. So the good news is that your nitrate levels are very low. I would say they're not changing a whole lot. There might be something going on here, but because it's a long-term monitoring program, I would wait another 10 years before I'd even say something's going on. And you could see that just the ambient nitrogen is a whole lot lower over here. It's a good news story than it is in our lakes in Rocky Mountain National Park. We've got another milligram per liter all the year long over there. So we're awash in nitrogen, and you are not, which is a good thing for you. So we looked at what that meant biologically, all this nitrogen sloshing around in there. And we did this with a bunch of experiments. And what we found is that when you add nitrogen to low nitrogen lakes over here, you actually increase biomass a little bit. If you add nitrogen and phosphorus, you increase it a lot, but nitrogen alone will increase the algae. They'll go, all right, this is good stuff, I'm gonna eat it. More importantly, it switched the algal species completely, whether you add nitrogen or nitrogen and phosphorus. We went from these very nutrient poor loving species, hundreds of them, to be dominated now by green algae and by a particular type of diatom. Neither of these types of algae that now dominate our lakes are very edible. So working our way up the food web, the invertebrates that like to eat algae and the zooplankton, they're not liking this stuff very much. So we have switched these algal assemblages by adding just a little bit of nitrogen over time. We've seen this in our observations, but we also did this with experiments. And I put this in because I think it's so cool. We never have much money, so we did this with tools at hand, and these happen to be hula hoops and PVC pipe. And what we did is we set out arrays of these in low nitrogen and high nitrogen lakes, and then we added little bits of nitrogen or nitrogen and phosphorus, or some were control. And what we found was, yes, indeed, you don't need very much nitrogen in nitrogen poor lakes to flip these algal assemblages over into something completely new that has never been seen before in these lakes for 12,000 years. What we've started to see recently in the past 6 years is this luxuriant growth on the shores of our lakes in Loch Vale and also all in other lakes along the Front Range. We've never seen this before. This is new. And this is a species, it's actually called Zygnema. Don't worry about it. It loves nutrients. What's changed? I mentioned before that our nitrogen's been high since 1950. So it's not that the nitrogen all of a sudden has changed. What has changed, however, is temperature. So our July temperatures, your July temperatures too, have gone up about 2 to 3 degrees, and our July water temperatures have gone up about 3 to 4 degrees over time. So what we think we're seeing right now is a perfect intersection of 2 global changes, nitrogen deposition and climate change, and it's creating something we've never seen before in these lakes. And we're trying to figure out what actually is going on. So one more of those kinds of slides, as I talked about moving up the food web. What we found is that when you add nitrogen to these lakes, you get more algae, but the particular kind of algae is very nitrogen rich. It's not very delicious to zooplankton. And what we're producing are zooplankton. That's my favorite. That's a little cyclopoid copepod, but there's lots of them down there. They're rich in nitrogen and they're poor in phosphorus. Now, nitrogen's the stuff of DNA and amino acids. Phosphorus is the stuff of bones. So if you're a fish, you need the phosphorus too. And we're creating, I've got a friend who calls this binge feeding on potato chips. If you're a fish and you're binge feeding on nitrogen rich but phosphorus poor, it's going to work its way up into fish problems sooner or later. We're not there yet. At least we don't know because we haven't done that research. But that's the food web of concern when you add nitrogen to these systems. So all of this nitrogen over all these years and all of the kind of research I've just described was published in the literature. And I give a lot of talks like this, and I was giving talks to many groups on the Colorado Front Range. And several of them said, you know, you're busy calling this change. This is all change due to nitrogen. And we think that's not change, it's damage. This is pollution. And so with a little help, and I have great respect for environmental organizations who take this watchdog role, they said, this isn't right. Rocky Mountain National Park is a Clean Air Act. It's mandated to be protected by the Environmental Protection Agency under the highest level of protection. And this is air pollution, and it's coming in and changing these systems. So thanks to Environmental Defense and Trout Unlimited, they pushed very hard on the Department of Interior. And what happened in order to try to resolve this problem is this amazing coalition by the Park Service, EPA, and the Colorado State Department of Public Health and Environment. They've created this memorandum to reduce the sources of nitrogen to Rocky Mountain National Park. It's called Nitrogen Deposition Reduction Contingency Plan. It goes on and on. And it started in 2007, and the goal is right now through voluntary measures to reduce the emissions from their sources so that we can get back to systems in Rocky Mountain National Park that look like systems that you have in the Maroon Bells and in the collegiates. And it's a very interesting coalition. We're doing this, some of it's happening because we have cleaner cars and we're switching from coal to natural gas and hopefully from there to wind and solar. So our nitrogen oxide problem will go away. I'm very confident that it will. And as it does, we reduce that source of nitrogen. Our big problem right now is agriculture, specifically feedlots and dairy. And we're meeting with them on a quarterly basis. We have a number of them, 75 actually, it's quite remarkable, who are trying to be part of the solution instead of being part of the problem. And all I can say is stay tuned. This is all voluntary right now. We're hoping that we don't have to go, or the state's hoping they don't have to go to some sort of regulation. I'm just providing them the data, but it's all very encouraging that people want to solve this problem. So I take us back to our lakes and to my great staff and students who do this work, and I want to thank you very much.
We have time for some questions, and in order to get those on the thing, we have to turn this thing to actually working. I apologize that it wasn't.
No, it's fine.
So, we heard you. So if you have any questions, I improve at any point tonight.
I did not. Would you like to describe?
Well, yeah, I might need your help. But she put up this sunlight data. I failed to include some important pieces of the story. So the Wilderness Workshop works with the Forest Service because the Forest Service has this project called the Improve Project, which is an air quality project that stands for
Interagency Monitoring of Protected Visual Environment.
And so part of that includes the air quality monitor up on Sunlight Mountain, not Sunlight Ski Area. No, never mind, I'm really wrong. Anyway, there's air quality, the data sheet was getting from Sunlight, I'm pretty certain it's from the mountain, not the ski area. And then we collect, the Wilderness Workshop collects the air quality, or deals with the monitoring equipment once a week on top of Aspen Mountain. And there's a funny device up there that's over by the top of the lift, lift 3. Above, right over there, there's a funny circular building maybe you've noticed and you're like, what's that? That's what it is. So we go up there once a week and change out the filters for the air quality data, as well as the summer lake data. So, and there's a lot more about it. Obviously, there's a lot more going on than I can explain. So, questions?
I remember changing the film. That's so fun.
Hi, Jill. That was awesome. Thank you.
Thank you.
I understand that the plant communities are also shifting because of nitrogen concentrations that end up that non-native plants, weeds, are better at utilizing that nitrogen than our native plants that grew up in a nitrogen poor ecosystem, and so this nitrogen deposition is also enhancing the invasion of non-native plants. Is this true? Did I make that up?
No, some of it's true. So it goes back to the strategies of many invasive plants, which is get in fast, and get what you can, and then stay there. And so a lot of invasive species have that strategy. So they're, just like grasses and sedges, able to take the nitrogen faster than the slower growing native plants. And I just saw, I don't even remember where, an amazing study that points specifically to cheatgrass, which we all know is a problem in the western United States. And cheatgrass responds immediately to nitrogen as well as moisture early in the summer, early in the springtime. So yes, in many cases, invasive plants get an edge if you give them fertilizer over native plants.
Hi, I'm curious about the lawn fertilizer and how effective.
Same stuff.
And do you have any data on how much is supplied and what sort of, we have such big cities and how
Yeah.
golf courses, just.
Golf courses.
Do a little better about your And
Death.
Susie can sum up the question.
Do you want to answer it?
No, I'm
Oh,
not
okay.
answering. I have a question.
Oh, okay.
No, I can't answer.
Yeah, death to golf courses, but at least fertilized golf courses. We did a study along the Colorado Front Range, so actually it was the whole Platte River Basin. And what I tried to do was quantify where the nitrogen, nope, I'm not going there. But yes, what we put on our lawns is you fertilize your lawns to make them greener. That's a good thing. You don't want to fertilize a national park. That's not a good thing. But when we fertilize our lawns, again, we're over-fertilizing in many cases. So it's running down into the sewers. Our sewers are directly connected to our rivers. And so we're adding the nitrogen to the rivers basically by wanting to have these green lawns. Urban areas are huge sources of that. And you add to that also something called impervious surfaces. So cities not only have lawns that everyone wants to look lush and green and flower beds, but they also have an awful lot of pavement. So instead of, when it rains, a lot of that runs right off into the rivers, into the sewer systems. And so it's fast tracking that nitrogen right to the Mississippi River Basin into the Gulf of Mexico. Or on this side, into the Colorado River Basin, where, it goes many places, but.
Some of it ends up in the Mississippi.
Does it? Yeah, because you've got all those diversions. Yeah. So I'm not sure I'm answering your question really well, but.
Well, I just wondered, you've got the data on feedlots and on cattle. I wondered if you had done any data on city applications.
We know that in most cities, the nitrogen flowing out of them is enormous. What I can't tell you is the comparison, although actually maybe I can. I just heard a lecture last week. There's one person for every 5 cows in the state. I might be wrong, but let's pretend that is. And a cow weighs, I don't know, a ton? So they're producing, and a normal person is say 100 to 150 pounds. They're producing that much more nitrogen in their waste that is going into the rivers than humans are. So cities are big sources, but in our particular state, feedlots are bigger sources.
That's what I wanted to know.
Okay.
Whether the lawn application was equivalent to the feedlot application, the actual lawn application.
And for cities, I'm actually conflating lawns as well as sewage treatment systems. So that's probably our biggest source of nitrogen is sewage treatment. And in some states, like North Carolina with all the hog farms, they actually have sewage treatment systems to manage those hog farms. And if you have tertiary treatments, you take the nitrogen out. That's more than you need to know.
So I was just curious about cumulative effects with reservoirs on the Front Range. You know, are they just serving as great repositories for nitrogen to slowly release it downstream over time? Are they?
Well, they do that.
Settling out? You know, the impacts of that stuff.
So the reservoirs that you see all along the Front Range are that beautiful hue of green. So they are getting fertilized not only with nitrogen, but lots of phosphorus coming in. What that does is it increases the productivity in these reservoirs, and that produces an awful lot of carbon. So one of the things fertilizing does is it causes a huge amount of carbon storage in reservoirs, which has only now begun to be considered in global carbon budgets. It's important. So you're sinking a lot of that nitrogen along with the carbon into the sediments, fills up the reservoirs. That's not a good thing. But it's storing carbon in a way that we had never done pre-reservoir development. And yes, some of it flows downstream. They're not stopping that nitrogen for very long. That might be it.
One more. Are there any strategies or techniques that can capture nitrogen in the system, that particular cover crop that takes it up, that we can harvest and then capture the nitrogen, or ways to treat water that aren't too invasive? I mean, I don't think we want to do a geoengineering in Rocky Mountain National Park, but these reservoirs, for instance, maybe are there techniques? I mean, short of reducing the sources, we need to figure out what to do with the accumulative mass of it.
So this is the most important question you can ask, is how do we solve this problem? And there are no simple answers. We really need to reduce worldwide the amount of reactive nitrogen. I was just mentioning to John before this talk. There are things that are being done with agriculture. So there are additives you can put in the soil that prevent the nitrogen from being sent up to the atmosphere as N2O, that really important greenhouse gas. There are new genetic ways of treating plants so that they're much more effective at fixing their own nitrogen. I've even heard that they've been able to put genes into corn that would allow them to fix their own nitrogen. Corn is our biggest problem in this country because we over-fertilize it throughout the Midwest, and that's a big source of the nitrogen going downstream. So if corn could fix its own nitrogen, that would solve an awful lot of problems. Precision agriculture helps to some extent, and the US Department of Agriculture talks about adding it at the right time, at the right rate, at the right amount, something else. There's 4 R's. And that actually helps so that you don't add so much that it flows downstream. We also need to start thinking about how to reduce our own consumption of nitrogen. I've been involved with Colorado State University. We just developed what we called a nitrogen footprint. So we calculated all the ways that nitrogen is brought onto the university and then leaves the university. And we're trying to see how we can actually fix that, you know, going from, we're developing wind power. So moving away from fossil fuels to wind is a big source. Putting more people on bicycles is a big source. Going to meatless Mondays is maybe the most important thing we can do. Reducing our food waste. Those are all things that we can do to help solve this nitrogen problem. But I think the problem is there's so many places that have to have intervention that I have a slide. What then must we do? If you go here, if we were doing the state of the art in trying to reduce all of the sources of nitrogen that go into the environment, at best we're only able to do those 4 wedges up on top. So at best we're only able to solve 25% of our problem by doing best available technologies and management today. That's a pretty depressing thing. I think we can do far better than that, but I think what we need are very creative ways of trying to think about how to solve this problem. And it may not all be technological, it might be social. We might need to have incentives to change our behaviors, or I don't know.
Well, with that, we will call it a night. And if anybody has more questions, you're always welcome to stay. And I know Jill will answer other questions. And the donuts appeared. Colorado was very late in delivering the donuts, but we now have donuts. So take one for the road.
Go for it. You don't need the microphone.
Okay. I want to end with one more thing.
Here you go.
Okay. One more thing, which is that the take-home message out here is that you guys are in great shape. I don't want this to be a big downer type of talk. You have an incredibly pristine ecosystem around you, and it's something to treasure and protect. So I'm happy to be here because of that.